Here is some help with the third test, and this time I'm going to use the key because it saves us some time and some calculations. I want to explain mostly how to get to these answers, or how to get the correct answer in a review of the concepts. So this first question says, what is the wavelength of a photon of electromagnetic radiation that has 6.24 times 10 to the negative 19 joules of energy? First thing to recognize is that you have a couple of equations that are going to seem very tempting. First of them is E equals h nu. E equals h nu is the equation that relates energy, E, with frequency, which is nu. Sometimes you'll see F, but you'll often see nu. H is a constant, it's Planck's constant, so you're going to have to know your constants or reference them, but H is one of them that you'll need to know, which is 6.63 times 10 to the negative 34 joule seconds. Another constant, by the way, is the speed of light. No matter what the light is, whether you can see it or not, it travels at the speed of light, which is 3.00 times 10 to the negative 8 meters per second. You might see it written as meters / second. You might also see it as a meter times an inverse second. Both are okay. So this equation you can't use because you don't know the frequency. But there is another equation. The equation that relates wavelength with frequency will come in handy because then you can derive or put together the equation you actually need. This equation relates frequency and wavelength. These are inversely related because you have c, which is a constant. So as wavelength goes up, frequency goes down. Or as wavelength goes down, frequency goes up. Let's take this equation and rewrite it. And we get that nu is equal to c over lambda. Now we can plug this equation into where nu is, and we get the equation we actually can use. Energy is equal to Planck's constant times the speed of light divided by wavelength. Now, ultimately, we want wavelength, and we are currently given energy. So you need to do some algebra, rearrange it, multiply both sides by lambda, divide both sides by e, and you get that lambda is equal to hc over e. If you don't see h and c given to you in the problem, that's okay, don't freak out. You have 4 things here, and you only have 1 number given. Very common for people to be like, what's going on? But just recognize that h is Planck's constant, so 6.63 times 10 to the negative 34 joule seconds. Speed of light is 3 times 10 to the 8th meters per second, and E is given to you as 6.24 times 10 to the negative 19. When you do this math, you're going to get a number that's in meters. And then you're going to look at your answer choices and be like, these numbers don't match. But you need to remember that meters can be converted into nanometers by using dimensional analysis. 1 meter is a billion nanometers. So in order to convert, you're going to take your number of meters, so whatever you get for your number of meters, and you're going to convert that from meters to nanometers by recognizing that 1 meter is a billion nanometers. And that's going to give you your answer. Number 2, calculate the wavelength in nanometers of the yellow light emitted by the sodium lights that illuminate parts of VT's campus with this given frequency. So now you're given the frequency, which is nu, and you're trying to find the wavelength in nanometers. So wavelength traditionally is going to be in meters, and then you need to convert. So we're going to use one of our equations we just saw up there. And this one, let's see, we have wavelength, frequency. So wavelength, frequency, it's light. It moves at the speed of light. So you need to rearrange this equation. And since you're solving for wavelength, you're going to get that wavelength is equal to c over nu. Let's double check our units because I'm a human who sometimes makes mistakes. So speed of light is meters times an inverse second, or you could just write it as meters per second. And then frequency is an inverse second. Recognize that an inverse second can also be written as 1 over s, and it's called a hertz. So that's the teacher could have totally put Hz for hertz because that's what an inverse second is. So if you see hertz instead of this, it's all good. All right. Now, with that being said, get rid of this. We have our units. Let's double check. So that's going to cancel, and good. We're going to have meters left over, which is what wavelength should be in. Except, remember, you want nanometers. So you do your math here. You're going to get meters and do the same thing we just talked about up in this part. Convert your meters into nanometers, and that's going to give you your answer. For number 3, it says the energy of a photon of yellow light is 3.37 times 10 to the negative 19 joules. And the energy of a photon of ultraviolet light is 5.88 times 10 to the negative 18 joules. And then you're looking at these two energies and you're asking which one has a higher frequency or lower frequency, higher or lower wavelength. So remember the difference between a direct proportion and an inverse proportion. So that's where our equations are going to come in. E equals h nu, that's going to relate energy with frequency. So energy, of course, is E, frequency is nu, and h is a constant. It is going to hold the relationship between energy and frequency. So as frequency goes up, energy goes up, or as frequency goes down, energy goes down. This means that this is a directly proportional relationship. Energy is directly proportional to frequency. So this wave has a higher frequency than this wave. That means that this one has also a higher energy. So it has a higher energy and it also has a higher frequency. On the other hand, this one has a lower energy because it has a lower frequency. But notice how it has a larger wavelength. So that relates to another equation. Actually, you don't need that one. Actually, you can use it. They both are all connected. So as we saw with the first one. So I can do the substitution thing again. E equals hc over lambda. This one relates energy and wavelength. So here, as wavelength goes up, energy would go down. Or as wavelength goes down, so as wavelength gets tinier and tinier, energy would go up. Notice how these arrows are now opposite. That tells us that energy is inversely proportional to wavelength. So let's look at these two answers here. Let's see. The first one says yellow light has a lower energy than ultraviolet light. So this number here is smaller than this number. So I'm going to put smaller than. Make sure you understand your scientific notation. So because yellow light has a smaller energy than ultraviolet light, it has a smaller energy, it's going to have a larger wavelength. So it has we can say larger or longer wavelength. And also thinking about frequency, as we just said, we can use this equation that relates energy and frequency. We can use this equation which relates energy and wavelength. And there's another equation that also relates quantities, and that's this one. C, all light moves at c, is equal to lambda times nu. And this equation, held constant by c, the speed of light, this equation is going to relate wavelength and frequency. And this is also going to be inversely proportional. So let's see, pick another color, blue and red. So for here, we have that wavelength is inversely proportional to frequency, which basically says that if something has a larger wavelength, it's going to have a smaller frequency, or vice versa. So let's actually keep with this example here. This one has a higher energy, a higher frequency, and clearly it has a small wavelength. On the other hand, just flip all those for the other one, and this one over here would have a lower energy, a lower frequency, and a higher or longer wavelength. That same logic applies. So comparing frequency with wavelength, we have frequency and wavelength. We know that they're inversely proportional, so they do opposite things in opposite directions. So the longer wavelength is going to be associated with the lower frequency. And that's why this is the answer. Number 3, which orbital has the greatest energy? This one's kind of tricky. The most thing I would say recommend that you do is review SPDF orbitals. We have an S here, we have a P here, we have what looks to be a D orbital, one of the D orbitals. Look at the fact that there are 5 types of D orbitals. One of them looks like this weird pacifier thing. But the way that I would think about this is imagine where the nucleus is. The nucleus is here for all of them. So which one of these has the highest energy? The one that can get you farthest away from the nucleus. It's kind of like potential energy if you think of it from a physics perspective. So the way that I think about this one being the right answer is that the electron cloud, the probability distribution of the electron cloud, is going to reach farther away from the nucleus. It's the biggest distance on the edge. It's just the largest orbital. You could also think of it as having the larger principal quantum number. It's just a larger orbital. That's one way to think of it. I could imagine this being on the test, being flipped, like which orbital has the smallest energy, and I would choose probably D for that. But this one is E because it's the largest energy, the highest energy, the one that gets you farthest from the nucleus based on the cloud that it's showing.